This presentation is on DDR2 and 3, and we'll be investigating many aspects of DDR2 and DDR3 and how our controller works with regards to DDR2 and DDR3. The agenda for this presentation is sectioned basically in two sections. One, we would discuss the basic DDR SDRAM, and we'll just talk about the organization and how the signaling works and how the read and write timings are organized. And on the second portion of this presentation, we'll discuss how the memory controller in PowerQuick and Core IQ will operate with DDR, and what are their features and capabilities working with DDR2 and DDR3. So the first section would be discussing the basic memory organization. Here you see a schematic representation of a single memory cell. The central portion to this memory cell structure is a storage capacitor. It's a very weak and leaky capacitor. One side of this capacitor is connected to VCC/2, and the other side would store the logical value depending on the charge being VCC or ground. The transistor that is used in here is an access transistor to allow the charge that is stored in the capacitor to flow to the other side, which is called the column line. So the transistor is turned on by the gate with using the row line, and the information is transferred to the column line. And the column line to store to read the value that is stored on the capacitor, the row line is activating the gate of the transistor, turning on the transistor, and allowing the charge from the capacitor to flow on the column bit. Before the transistor is turned on, the column bit is pre-charged to VCC/2, and the line is momentarily removed and left floating. However, the parasitic capacitor on the parasitic line capacitance will keep the charge or voltage that is on the line, and when the read voltage, the charge on the capacitor will influence either increase or decrease the VCC/2 voltage on the column line. That change in voltage is sensed by sense amplifiers or sense amps, and they'll store in a row buffer. So a single memory cell is not sufficient. They are organized in row and column fashion, as you can see it. It's a two-dimensional array. The address that is going to locate the memory location is sectioned in two parts. It's decoded into rows and columns. So when a row is selected, all the transistors that are on that row will be activated. Hence, by activating a row address, all the information on that row will be transferred by sense amplifiers into the row buffers. However, the organization of this two-dimensional array is limited, as the number of rows and columns cannot be increased indefinitely. To increase the memory size, we add more of these two-dimensional arrays, and we call them banks. And the other advantages that this would have is that while operating on one bank, it could also simultaneously work on other banks. So it will increase the performance of the memory. The operation or accessing a memory is always starts by an active command taking the information that was in the two-dimensional array into the row buffer. Once the information is transferred into the row buffers, the information is no longer available in the two-dimensional array or bank 1 as it's depicted here. Next, to do any read or write operations, the column address of where to begin reading that information from the row buffer is provided, and all the read and write operations happen on the row buffer itself. Once the information has been read or written to, and we no longer need the row buffer, we close it, or it's called, this action or this command is called a pre-charge back, so the information is restored back into the two-dimensional array. Here you see a single SDRAM. It's a DDR2 SDRAM, and in addition to information provided in this slide, I'd like to point out that there are two memory banks, or there are two memory bus that I'd like to point out here. One is the address bus, which consists of the DQ or the byte, and DQS or strobe, and data mask or DM. All these signals operate together as a bus, independent of the other signals. The other signals, which are address, command, and control signals and clocks, operate as the other bus, which is called the address and command bus. The address and command bus is signaled or sampled by the clock signal, rising edge of the clock signal, and the data bus is sampled by rising edge and falling edge of the strobe. A single byte of memory is not sufficient, so they are organized in a concatenated fashion to increase the number of bytes in a memory. There are 60, here you can see a 64-bit bus, which consists of 8 byte lanes and an additional ECC byte lane. And as you can see, all the address and command bus are all connected to all the SDRAMs to the same locations. The only thing that is different here is between connections for these SDRAMs are the byte lanes. The order of the byte lanes, as you can see, they are different. Here is a basic chart of commands, and I like to point out that the commands that are sent to SDRAM are all active low. Here we have chip select, row active select, column active select, write enable, and they are all active low. In an active command, we want to open a row. So we select the chip select that we want to access, and the row access select is pulled low to indicate that we are going to select a row from the memory. And as you can see, the read and write commands, they have the column access select low, meaning the operations of read and write occurs on the column, or once the memory has been the information in the memory has been passed into the row buffer. The pre-charge or closing of the row buffer is, again, it needs to access what row put that information back in there. So we have the row access command activated low here. And you also have pre-charge all and refresh commands here for your reference. Read and write occurs in bursts. They do not happen in single byte reads or single byte writes. It happens in burst, and the bursts are the information that is provided for the read and write is the beginning address of that burst operations. There are 4 beats or 8 beats of transfer of data every time, depending on what the memory selection allows for 4 bursts or 8 bursts, or if both burst types are available, which one is selected. So in a 4 burst, we transfer in a 8-byte lane or 64-bit data bus, 32 bytes are transferred, and that would take 2 clock cycles. 8 burst will transfer 64 bytes, and that will take 4 clock cycles. If you're using a 32-bit wide memory bus, then 8-bit burst will indicate 32 byte of transfer. Here is a retiming example or a diagram that you can see it's depicting the active commands, and while the active command is sent, the row and bank information is also sent at the same time. And this bus, which consists of the column, clock and command and address bus, are all sent at the same time. So the next certain amount of clock laters, which is the predefined JEDEC amount of delay between the active and read command, the read command is sent. With the read command, the column and bank information is also sent to tell the SDRAM what bank to use and what column to start sending the data from. So from the very first read command, on the very bottom, you see the DQS DQ signal, which is the data bus. Cast latency later, which is 4 clock cycles here, the data starts streaming out. And on the rising and falling edge of the strobe, you see that the data is flowing. You also notice that the strobe and data are edge aligned when they're sent during the read by SDRAM. So the next command here is another read, and because they're concatenated, that means the addresses or the columns selected here are next or the consecutive addresses that were already used. The information will flow in here, and after 4 beats that you can see on the bottom, that the DQ is going D0, D1, D2, and D3, and then starts the next read, sending the information for the next read, which would be D0, D1, D2, and D3 again. Once the read operation is completed, here we have a pre-charge command which would close the row buffer that was open and restore the information from the row buffer into the memory cells again. Here is a timing diagram of DDR3. There is basically no difference between DDR2 and DDR3, except a few detailed differences. The differences are that the number of beats in DDR3 are always 8 beats. And as you can see, once the read command has been issued, there are 8 bursts that are happening. And the other information to notice here is that the again, the same as DDR2, the strobe and data are edge aligned as well. Next, we're seeing another timing diagram here, and this is just the write timing diagram. And as you can notice on the address and command bus, we see again the active command starting the operations. Active command opens the row buffer. Once the row is opened, the operation on the row can occur by a write command by providing the column address. Then a write latency later, that data will start to flow from the controller, memory controller pins. And one thing to notice here is that on the data bus, the strobe signals, the rising edge of strobe is center aligned on the data I. So similarly for the falling edge is also center aligned on the data. And the reason for this is that memories are simple structure devices, and there's no delay or managing of signals occurs in DDR or SDRAMs. So the strobes are sent right at the center of the data I, so the SDRAMs can sample them as the data and strobes arrive. Similarly, here is a DDR3 timing diagram, and here again, as indicated before, the burst for DDR3 are only 8 beats, and there are no 4-beat selections. We'll discuss this further, but just keep in mind that DDR3 is always 8-beat bursts, and so as you can see, there are 8 beat of data on the bottom for the data. And the second thing that you can notice is that the preamble, or the signal that is sent before the strobes are center aligned for the data, it goes about half a cycle high and then half a cycle low. So as we discussed, the burst length for the DDR3 is always 8 beats. Now, there are options that are called burst chop or on-the-fly burst chop modes of operations. And what happens is that in some cases, we do not want to send 8 beats of data. And in some cases, it is advantageous to send only 4 beats of data, where the turnaround times between read and write will improve the performance. And that is case by case basis, and that is device dependent. So if burst chop 4 or on the fly burst chop 4 is selected, the 8 beats still occurs, but the data will only be carried on the first 4 beats. The second 4 beats would be just no data. And as you can see on this diagram on the bottom, it is called the bubble. And so a read command is sent and another read command is sent. And the distance between the 2 read commands, again, is going to be 4 clock cycles. The diagram here displays a quick comparisons between all the DDRs, DDR1, 2, and 3. The package type has been moved to, as you can see, is moved to BGA only. The voltages have reduced from going from one generation to another. The densities have increased. The number of banks have increased. The prefetch values have increased. The data rate have increased. Read latencies or cast latencies also increased. The write latencies have also increased, but they've changed from DDR2 to DDR3 in a different manner that you may want to make a note of. Also, the I/O signaling has changed as the voltages have dropped. So we're still using the SSTL in a different formation, which is different voltages. They're JEDEC defined parameters. Next, the termination has changed from DDR1 to DDR2 by introducing the on-die termination for the data and strobe. However, on DDR3, when you're using a DIMM, because of the flyby topology, the termination for command and control and address are also provided on the DIMM. The data strobes have moved from single-ended to having a choice in DDR2 between single and differential only in DDR3. In this section, we are going to discuss the signal and termination, electrical signaling and termination of the DDRs. Here is a diagram, a table for the different voltages for DDR1, 2, and 3 that are very useful to make a note of. Something to pay attention when you're designing your DDR subsystem is that please be careful with the VREF. Make sure that you, if from all the signals that you pay attention to, the single signal that you need to pay attention a little bit more is VREF. VREF is VDD over 2 and is expected to track the VDD. Here's a diagram of the transmit and receive, and as you can see, all the voltages that were defined in the previous table, they're depicted here to show what each of those values or parameters indicate. Again, if you pay attention to the VREF on the receiver, you can notice that there's a DC component and there's an AC component that needs to be followed, and the limits needs to be maintained. In DDR, unlike other interfaces, the impedance matching is required. That would mean that the reflection must be reduced to 0, and based on this formula that you see on this page, that would mean that the load and the output impedance of the driver must match, and when they match, the reflection would be 0 based on this formula. And here you can see there are different ways that you can provide that impedance matching. There's a single resistor matching that you can do, or you can do Thevenin equivalent of 2 resistors, or you can do resistor and capacitor. And also here I have provided additional termination that are allowed in SSTL spec, and the only reason I put this here is to indicate that there's no single correct way of doing this. There are so many different ways that you can do this. However, please abide by JEDEC rules, whatever termination scheme you're using. Here is a diagram of DDR1 termination. DDR1 used the resistors or terminations on the board. There were none of these termination resistors were embedded inside the SDRAM. So the number of terminations were very high, as you can notice here. All the signals had to go to a voltage island or voltage bank termination of VTT, which is VDD over 2. And there were also series resistors that had to be used. When we moved to DDR2, the termination for data bus was moved inside the chip, and the on-die termination was used both in memory controller and in DRAMs. So the number of termination resistors that were used on the board was reduced. And in DDR3, if a DIMM is used, then there are no termination required on the board. However, if you are not using a DIMM and you are going to lay all the SDRAMs on your board, then pay attention to the VTT termination for address and command. On the on-die termination is a way to reduce the amount of power consumed and also improve the signal integrity on the SDRAMs and memory controller. Here, as you can see, the termination resistors are turned on and off by ODT signal, and the ODT signal is sent just prior to a read or write command to activate these termination resistors. Once the read and write commands are performed and the data has been received and transferred, then the ODT will turn off and these resistors are disconnected from the source, hence not drawing power. The differences between DDR2 and 3 that there are different termination values that are available. The table shown in this picture is a DDR2 suggestion or recommendation by Micron for 2 DIMMs operating at 533 data rate. Now here we're going to talk about the features and capabilities of power-quick DDR controllers, or the Core IQ DDR controllers. This is the second portion of this presentation. So we're going to switch gears and talk about what are the capabilities of controller, what are the features that are provided in our controller that operates with DDRs. What is common, what is listed here on this page are all the items that are common among all the controllers, memory controllers that are provided that offer either DDR1, DDR2, or DDR3. So they all support JEDEC standards, and the memory devices densities are supported up to 4 gigabit, and the data rate is supported. The data rate is different from device to device. Please defer to the datasheet for the device to find out what is the maximum DDR data rate operations for that device, the specific device. The number of rows and columns are also supported to the maximum, and the data mask signaling is also supported for when less than sub-double word writes are written. It means when you're sending information less than 60 or 64 bits or 8 bytes, then a mask would be used to prevent the writes for data that you're not writing. Up to 4 physical banks are used, or we call them chip selects. Each chip select would have its own row buffers, and it would have its own banks, sub-banks. There are physically up to about 8 gigabyte and a total of 16 gigabytes per controller. The interleaving between the 2 chip select or 4 chip selects are available. Memory controller interleaving when more than 2 memory controllers are available. That means if the device that you're using has more than 2 memory controllers, interleaving between the 2 controllers are also provided. Unbuffered or registered DIMMs are supported as well. Continuing the same feature list, there are up to 32 open pages that could be allowed if all the chip selects are selected. And auto pre-charge, which means automatically closing the open row buffers as a function after a read or write happens. After a read or write command is also available. Self-refresh, which is to maintain the DDR content while you are either going into a power management mode or you're powering down on the controller side, is available. Up to 8 posted refreshes are available. The automatic or software controlled memory device initialization is also available. The automatic initialization is a very nice feature where you don't need to worry about all the details of JADEC required steps to initialize the SDRAM. All that is done automatically. We also have ECC available. 1-bit error correction detection is available. The 2-bit error detection is available, and all errors within a nibble or 4 bits are detected. We also have ECC error injection, where you can test your system by injecting ECC errors. And also when using ECC or when ECC is enabled, all read modified writes would happen for any writes that is smaller than sub-double words. The automatic data initialization for ECC is also available. This is a very nice feature where you want to initialize the entire location or the entire SDRAM area, and all you need to do is select that bit that does this, and after initialization of the memory controller, it will initialize the entire SDRAM for you with the value that you want. Dynamic power management is also available. Now, all these features up to now would apply to all DDR1, 2, and 3, and for all memory controllers that we have or we provide. Now, the information in this slide would provide all the features and capabilities that are common in controllers that support DDR2 and DDR3. This would include the Core IQ as well as power-quick devices. There is a partial array self-refresh available that in case you don't want to refresh the entire SDRAM area or memory space, you may want to do a bank or select a bank from that memory area and only refresh that and let the other banks to lose their content. This feature would be useful if we're talking about very sensitive applications where they need to manage power even in very small, minute levels. And this feature also makes sure that if you want to use this feature, the SDRAM must also support it. Next, we have the address and command parity for register DIMMs. We have ECC available for the data bus, but there's no ECC for the command and address bus. But if you use register DIMMs, the option is available. This feature would apply to both DDR2 and 3. Independent driver impedance setting for data address command and clocks are available. Previously, this was done by a single setting for all the data and address and command and clocks, but now you have selection to select different drive strengths for each of these signals. Mirror DIM is supported. I will touch on this in future slides. There is automatic CPO or cast to preamble override, and I will also touch on this on future slides. And also write leveling for DDR3 is supported or available, and we'll discuss this further as well. Then there's the feature of providing the automatic ZQ calibration for DDR3. So as this is a specific feature for DDR3 that is not available in DDR2. This feature was added into JEDEC for DDR3s, where you could dynamically calibrate the driver strength of the SDRAM on the DDR3. And this feature is very useful because as the voltage signals are lowering and as your timings are shrinking, you would need to rely on a very good and trustworthy calibration method. And this method is initialized during initialization, and our controller is capable of providing the commands to set the DRAMs into modes that they calibrate themselves. Fixed or on-the-fly burst chop modes for DDR3 are available. We touched on this briefly, and as you know, the DDR3 operates only an 8-bit burst, and with this you let the memory controller to decide either to send 4 or 8 bursts, and that's on the fly burst chop mode, or you can select a fixed burst chop mode where you would select a 4-bit burst chop send or a fixed 8 bursts in DDR3. The synchronous reset for DDR3, this is a feature, a synchronous reset for DDR3. This is a feature that is in the DDR3 SDRAM. The controller does not control this command. This is not a command that is sent by the memory controller. However, a reset pin is available on all SDRAM DDR3s. And what you need to do is make sure that this reset pin is connected properly to a controller within your board to give you the capability to reset the DRAMs or DDR3s when you need to. And there's also a sequence that needs to be followed to be compliant per JEDEC. So you need to study that just a bit to understand that this feature is available, and it's a very good feature to take advantage of. Synchronous and asynchronous clocking operations are available. All this means is that you can either provide a specific clock for DRAMs that would operate at high frequencies that are normally allowed, or if you use the synchronous mode, it just means that there's no external clock is required. The internal clocks are used, and you would be limited to the clocks or frequencies that are provided by synchronous mode. So just two different clocks options that are available. Here we're going to discuss the flyby topology a little bit more and find out why we need a right leveling. The flyby topology or architecture was introduced in DDR3 to change the way the address command and clock signals are routed on the board when connecting between the different SDRAMs. So in DDR2, we had length matching between clock commands and control signals, where all the trace lengths were equal length from controller to each SDRAM. And but in DDR3, because the speeds and are increasing and voltages are reduced, they introduced the flyby routing, and that is the recommended and mostly followed topology for DDR3, that all the address and command and clock signals are sent from starting from the first DRAM to next, and to the last SDRAM, and there's a single termination that is used for all the signals. The motivation for this flyby topology was to improve the signal integrity, and as you can see here, the flyby topology does improve the signal integrity, and the data eye is much wider than on the right than is on the left picture. So when right leveling occurs, or this flyby topology is happening during a write cycle, the skew between the clock and strobes are increased due to this flyby topology. Now what we do is we do a write leveling, whereby we remove these delays or compensate for these delays by changing the timing for each byte lane. Now this delay or skew that is introduced because of the flyby needs to be managed during the read and write. Here you see the read adjustments, or the methods that we use to adjust during the read cycles. So as you can see, the commands would arrive to the first DRAMs, and then as they progress and propagate through this through the line, and they will reach to the last SDRAM, the command will arrive at each of these SDRAMs at different timings, and they would issue their read, or they would send their information on the data bus at different times. So what we do in our controller is we have a timer for each byte lane, denoted by CPO value, whereby we'll tell the controller that when to expect each of these byte lanes to arrive, and hence we compensate for the skew that was introduced based on the flyby topology. During the write cycle, all the data would be sent. If all the data are sent at the same time, then the SDRAMs would not expect them at the same time because of the skews that are present in the command structure. So what happens here is, during the initialization, the memory controller figures out what these delays are and would send each byte lanes at a different time with a needed delay to compensate for this flyby skews introduced. And all we need to do in memory controller is select the right leveling, and this process occurs automatically during initialization by the memory controller. So as you can see, both read and write are compensated for automatically, and a simple selection of this automatic adjustments would take care of the skews that are introduced by flyby topology. The DIM mirroring, or mirror DIMs that you can buy are so when you purchase a DIM and it specifies in the datasheet that it's a mirror DIM, it indicates that there are two chip selects or two ranks available on that SDRAM, and the routing that is done between the two ranks are so that the stubs are reduced and the traces are reduced by switching some of the signals so there's no cross connection required, and that would improve the signal integrity. So this is nothing that you need to do. It's just if you purchase a mirrored DIMM, then you need to make sure that you have selected the mirrored DIMM register in the DDR to tell the memory controller that the memory used it's mirrored, and the signals would automatically be switched to compensate for that adjustments that is done in the mirrored DIMM. So in this section, we're going to talk about the initialization and register configuration. The initialization flow for DDR2, as you can see here, is power up and wait for the DDR controller initialization. Once the stable clocks are available, wait 200 microseconds, and then set the map enable to enable the memory controller. Once memory controller is enabled, then it automatically does the following, which will pre-charge all command descent, which would close any open row buffers. It would initialize the DRAMs, and after a certain amount of delay that is required in the SDRAMs, then it would be ready for operations. So basically this timing diagram or this chart will show you the flow of operations, but there's nothing that you need to do after memory controller has enable bit has been set. In the DDR3, the flow is very similar. All you need to do is power up, set your registers in DDR, give it some time, and set the mem enable. And once that is done, then the rest happens automatically by memory controller. There are two types of memory registers when you're trying to set your DDR configuration. I would divide it into section that is provided by the SPD, is predefined in the datasheet and the DRAM datasheet, and those values are just making sure that you follow the parameters as indicated in the DRAM datasheet. Then the second portion, or this second group of registers that you could program, are non-SPD, whereby you are providing information to controller to tell it to manage certain aspects in a different ways. Here we have the on-die termination, we have driver impedance, we have the clock adjust, write data delay, or cast preamble override values, or the 2T, 3T timings, whereby you are sending the address and command in 2 clock cycles to increase your address and command I. Also the burst type selection or write leveling start values. So these are the list of the items that, examples of items that you need to set or select based on the activities that you want to do, or the selections that would best fit your application. So how do we adjust or optimize these timings? The parameters that are not part of the SPD. Here are the list of items that you need to pay attention to: clock adjust, write data delay, CPO, 2T, and write level enable, and the burst chop mode. So details of each of these would be that clock adjust is that you need to shift the clock so it is center aligned to the address and command bus. As we discussed earlier, SDRAMs are very simple devices, and we need to provide informations or the clock and the data, clock and the address and commands in a fashion where they just need to, as soon as they see the rising edge of the clock, they will sample the information for address and command lines. So usually, if the clock adjust is not set to, or is set to 0, or is not set to any value other than 0, all the address commands and clocks are sent edge aligned, and I would expect that that system would fail quickly. So the clock adjust value needs to be set to half, as depicted in here, or you need to adjust it in a fashion where it's centered on the command and address bus. The clock adjust is a register field location in a memory controller where you can select different delay values. The next item here is write data delay, and write data delay is shifting the address byte lanes to compensate for the TDQSS requirement by JEDEC. So the strobe and the clock are not way off from each other, but maintained within the quarter clock. So when you're setting your clock adjust, just make sure you check it on the scope and make sure that it is center aligned. The value that you have selected would best center align the clock on the address and command signals. Similarly here, you want to check the skew between the clock and strobes, and to modify this skew, you can write data delay, and you can again check this on scope to make sure that the selection is valid. Here we also providing information on CPO. What we need to be careful about CPO is that if the auto CPO is not selected, and auto CPO is available on all devices that provide the option for DDR3. Most of our memory controllers provide an option for two types of memory, either DDR2, DDR3, or DDR1, DDR2. So the controllers that do support DDR3, but you're not using DDR3, you're using DDR2, you may select a CPO value based on this table, and the calculations also provided in the application note 2583. However, if you have this option available, you have the automatic CPO calibration available, I suggest use it because it does provide an automation system whereby each byte lane would acquire its own delay or timing value. For DDR3, that is almost a must. So if you're using DDR3, automatic CPO calibration should be used. 2T and 3 timing are options that are available for you, and it shouldn't be used with register DEMS, and we typically use 2T timing is when more than 2 ranks or 2 chip selects are used as a load. So the more heavily loaded systems may require 2T timing. Now here are the section that we're going to talk about all the pitfalls in debug that we've experienced during years of working on memory controllers and SDRAMs. Number one item would be that if there is a power on configuration pin to select a DDR type, make sure that that configuration is correctly set. So if you do not on the board itself, you should provide an option for the configuration of that pin. Next, we're going to talk about the ECC. So if this is one single most important part about DDR subsystems, it doesn't matter if you're using our parts or some other parts, but ECC is very important in debugging any failures that happen in DRAMs, unless do provide the ECC in your system as a good feature. And as you can see that we have this feature available, and it can detect errors and correct errors, and setting these making sure that you have ECC option available on the layout of the board, so you can select this ECC errors. The other pitfall is that making sure that the write latency is correctly programmed. The cast latency is not selected too high, as you would use devices that are faster than the frequency you are going to operate them at. The SPD values for the cast latency would be the highest value. So you may want to reduce the cast latency based on the speeds that you're running the DDR. And also make sure that the correct ODT settings are used. The next one is to pay attention when you're programming the cast latency, burst latency, write recovery, active power down, and additive latency or differential DQS enable. So these are fields in the memory controller in the registers that are used in two sections. They're used in memory registers and also used programmed. The same values are programmed in the mode registers. So make sure that you provide the same values between the two fields when you're programming a single parameter. There are timing parameters and settings in DRAM memory controller where there is a minimum value for each of these parameters defined by JEDEC. So based on your timing parameter, based on your SPD value and dividing it on your timings, you may come up with a number of clock cycles that are less than 2 or 4 based on using DDR2 or DDR3. So make sure the minimum value has been observed. There is a 200 microseconds or 500 microseconds for DDR3 delay required between after you set your registers and before you enable the memory controller. So make sure that is that step is observed in your software. Now here we're going to switch gears and discuss the pitfalls that are used on the board. And here are the list of all the debug features or pitfalls that we've noticed during years of experience. And the list is provided here, and I'm going to have a slide for each of these and discuss them. So this is for your reference, and we will discuss each of these in shortly. The first one is to make sure that MVRF is not noisy. So this is one signal that you want to pay attention to. Keep it away from all the other signals, and make sure that you provide enough trace width so there's no current starvation. Although these are very low current consuming signals, you just want to keep it away from other signals so there's no noise, additional noise coupled on them. When you're measuring the VREF, make sure that you measure it at the decoupling cap for the VREF. Measuring the VREF at any other point would not show you a valid information. The other information here again on VREF, as you can see, the trace that is highlighted as a red line or red signal in this board layout, it is away from all the rest of the signals. It is definitely selected to be wider or have a wider width than the rest of the signal. And make sure that you provide the capacitance that is required. Another feature, as you can see, we're discussing VREF in detail in different aspects, and the emphasis is that this one signal is the deciding factor for all the SDRAM and in our controller. And so it is very important to be paying extra attention to this one signal. So here we're discussing that do not use a current a VRF DC-DC generator that does not provide enough current. We do have spec in our hardware spec that specifies the amount of current that is required for VREF for each device. So make sure that has been observed. The other pitfall would be that make sure to avoid cross-plane splits, and make sure you avoid trace over and reduce the if you avoid switching, or if you have to make sure they're not over each signals from the different levels. The other aspects that you need to pay attention to are the spacing between each of the byte lanes, and following the rule of trying to make sure that say if you need to if you're using DDR2 and you need to trace match the length between the traces, then you follow each byte lane separately and start with the farthest byte lane, then work your way to the closest byte lane, and make sure 10 mils is spacing is observed between the byte lanes, and there's a half an inch spacing that is or the skew between all the byte lanes does not go beyond half an inch. Do not forget your terminations. Here you see the terminations that is for DDR3 specifically. That is, we've noticed that people might miss or try to configure them similar to DDR2, and that is not correct. So pay attention to the termination required for DDR3 once they get to if you're laying out the parts on your board and you're not using a DIMM. The other important feature, again, this is to re-emphasize what was discussed previously, that if you do have, for DDRs, there's a selection between DDR types. That is a pin that needs to be configured on the board during power on, when the board is being powered on. So make sure that that pin has been brought up and proper pull up and pull down is applied. If you're building a board and you are considering an option to keep it for a while and expand the memory size, make sure you leave options open for yourself and leave the the footprint available so you can use to expand it by using soldering different DRAMs at a later time. Only use the topologies that are approved by JEDEC. There are many ways that you can route your system or DDR subsystem, but please do follow the JEDEC approved topologies. Do not separate your power planes. DDR does provide two different power planes. It calls them VDD and VDDQ, but we do not want to separate these two, and we use a single power plane. When you're using your calculations or timing budget, do include the slew D rating for setup and hold depending on the slew rate of the device that you're using. Also, an important information to note that if you're soldering your DRAMs on the board and you're doing your own layout, make sure you bring out, because all the DDR2 and DDR3 parts are BGA, and there's not going to be any access to reading the signals when you want to troubleshoot. So there are predetermined ways that you can bring these signals out, and JEDEC approved ways that you can bring these signals out. And so if you are going to debug and you're considering you like to monitor these signals, make sure you bring the signals out. This concludes my presentation. The important information or very important references are listed here on this page for further studies. I do highly recommend that if you're using DDR3 for layout design consideration, consider the application note 3940 and to provide you with a guideline to how to set your register settings for DDR3, use the application note 4039. Thank you very much.